Bob's talked about the kind of macro aspect of what we're all here about, and I'm going to the opposite extreme and talking about a particular aspect. Notes on step tiles. These are just comments from me. It's not how to design step tiles, and it's also, I'd like to emphasize, my opinion. It's been gained over a number of years of trying to do these things. So, what is a step tile? Wrong button. When referring to a step tile, the accepted default meaning is a hull having one or more transverse steps. Some talk about longitudinal steps, which have a similarity to spray rails running down a boat. But in this presentation, I'm only talking about transverse steps, the main idea. So these are the transverse steps. Some people refer to these as longitudinal steps when the hull is split up into one or more longitudinal surfaces which have a greater vertical displacement than just an ordinary spray rail attachment. But transverse is what we're looking at here. That's Beast at the Seablade 40 at HSBO 2 years ago, and shows the hull that we're talking about, and that's just the basic. In case anyone doesn't understand what I've said, that is the basic transverse step. The advantages of stepping your hull, my opinion, you get a drag reduction of between 8 and 12% when the craft is planing. It depends on how good the basic underlying monohull was that you started with. Because when I don't know about others, but when I'm designing a stepped hull, I design a basic monohull first, and then in the design process adapt the steps to it. The other advantage, main advantage of pitch reduction and improved pitch control in a seaway. You get an increased resistance to porpoising, but that's all part of the pitch control, basically. The disadvantages, takes more design effort to get it right. We can't use water jets. The aeration caused by the air fed in under the hull by the step arrangement, and they have to ventilate to work. The air mixed in with the water travels into the intakes of the water jets, aerates the impeller, and causes ventilation or cavitation of the impellers, which mucks up the performance of the water jet. So at the moment, step tiles and water jets don't really go together. Various people are working on that aspect, or having semi-stepped hulls. But when you semi-step a hull, i.e. sort of step in from the outside, but not the centerline part where the water jet is, you get limited positive results. The step tile's directional stability can be a problem if you don't take care when you're designing it. Sometimes you can have trouble getting on plane, but not often. That's usually a ventilation problem if you do, i.e. lack of ventilation problem if you can't get your step tile on plane. It's not usually the case with monohull type craft. You can get more drag at displacement speeds, and if you've got a boat that has to do a lot of work at displacement speeds as well as planing, then you need to take the extra drag into account. Why do we get the extra speed or reduced drag? The higher wetted aspect ratio of each individual surface improves the pressure on the hull, improves the lift per unit area, so you need less wetted surface to carry your load, and therefore you get less frictional drag. The aspect ratio is wetted beam divided by mean wetted length. So wetted beam divided by the length. And so the higher the aspect ratio, the wider the beam for the length. and the more efficient the lift you get. There are things that restrict how far you can go with that performance problem. But that's, broadly speaking, the shape of the wetted surface underneath. Speed range, speed length ratios, V over root L, 5 to 6, Froude numbers 1.5 to 1.75. That's where I reckon the advantages, performance advantages, start. You can still get some trim control benefits below that speed, but your efficiencies are not going to be much of an advantage. And as you get slower, then they become a disadvantage. The steps become a disadvantage you compare with a monohull for low-speed planing. The pitch control, which is such a good part, such an advantageous part of stepped hulls, is important. How do we get it? With a non-stepped hull, the pressure from the wave that you hit travels along the hull from bow to stern, lifting the bow. So that pressure is constantly lifting the craft as it travels back towards the centre of gravity and accelerating the bow skywards. By the time it's reached the centre of gravity, the upward momentum is quite high, well established, so that the pressure wave travels past the CG, then it starts lifting the stern, but by the time it starts lifting the stern, the boat is travelling upwards and beginning to clear the water. So you get to a high pitch angle. You will leave often at a high pitch angle, catch the stern when you come down, which then pitches the bow forward. You get a lot of amplitude change. You get this kind of thing. It's pretty rough weather, and one of the kind of Torquay powerboat races, classic monohull racer by Don Shed, and it's rough, but it's exhibiting the sort of motion that I'm talking about. With a stepped hull, the wave pressure skips rapidly from one surface to the next surface, and what happens is when the bow hits the water, starts to lift like an ordinary monohull. It then reaches the first step, so the lift ceases, and so the input ceases, having raised the hull a certain amount at the bow, but not a great deal. So the input stops, then the wave contacts the next surface back, which is much closer to the centre of gravity of the hull. So it then tries to lift the boat bodily. It doesn't pitch it up, it tries to lift the boat bodily, and so your pitch angle is not so great. It then skips again to the aft surface, behind the aft step, and that gives the stern a kick. So the result is that the pitch angles don't change anything like so much as with a non-step monohull. We're talking like for like. There are other ways of reducing the pitch of non-step monohulls, trim tabs and other things, trim control on drives, but I'm talking about the hull itself and how it controls this attitude. And this system, pitch control system, also gives the higher resistance to porpoising and those problems. This is a stepped hull running in reasonably rough water, and this is a Scorpion race rib. And has been very successful in the past, and its pitch control in rough water often allows it to beat other much bigger boats in those conditions. And you can see the attitude. You leave the water, you platform across tops of waves, but you don't have great changes in pitch angle. It's much more controlled. Just an aside here. People who talk about steps and wetted surface under the hull often draw this picture. They'll draw the monohull without the steps, where you have this shape continuing all the way to the aft end, which is broadly correct for the wetted surface on a planing hull. And then they'll draw a stepped hull and say, this is what the wetted surface looks like underneath a stepped hull, but it's not correct, in my opinion. Anyway, this is what the shape looks like, much more the the leading edge shape there broadly matches the shape of the trailing edge of the next wetted surface ahead. So that broadly matches this. This is given by Navitec. It's a CFD picture, pressure distributions, which broadly shows this shape that I'm talking about. Speed and handling. The further aft and deeper the steps, and the more your drag reduction, the faster the boat is, but the worse the handling is likely to be. So as with everything, it's a compromise. The deeper steps allow the boat to run at a higher angle of attack. You get smaller wetted surface area because of the pressures on those surface areas, wetted surfaces are higher. So if we lead a smaller area, you get less friction drag, but the forward surface is carrying more of the load, contributing more. And because the steps are deep, because the steps are deep, the aft surfaces are likely to be shielded by the forward surface, and therefore they are less in contact with the water. This is no drag, means or reduces the drag at the aft end, but you get no location in the rear end either. So lateral location is lacking. So the boat lacks or can lack directional stability, which can cause problems, as we know some people have met up with. So generally, you can get away with an aft center of gravity position for a light boat, which is light and quick. The steps can be aft because everything's aft. Even the forward step wetted surface is back towards the stern. You don't need so much area for your lift. You've got a light boat. But if you've got heavyish boat and forward LCGs, you need the steps to be moved forward. Otherwise, it's the forward step that does all the work, and the rear steps, the rear surfaces get shielded. So this is broadly illustrating what I'm saying. As the steps are too deep, you don't get much of this in the water. You don't get much side area in the water. So shielding the aft surfaces reduces the drag, but the hole it creates reduces your lateral location. You need the side area to give you that directional stability, the fin effect, like the flights of an arrow. You need that to hold you straight. Otherwise, you have this tendency for high-speed broaches. This is all part of getting the design right. So if you allow the back end to be well in contact with the water, if the aft step's not too deep, then the aft surface will be in contact with the water over a reasonable distance, and therefore it will have enough lateral contact with the water too to hold you straight. You shift the emphasis, take some of the lift off the forward surface and put it on the aft surface. It's safer that way. It's not always the most efficient, but you still get an efficiency gain. You have to control the boat in roll as well. And because the pressures on the bottom are higher with steps, the boat's liable to be higher as well in the water. Chine rails are important to control the roll. If the chine's clear of the water at high speed, then you need an outside spray rail to control the water. You need an outside edge. You've got to catch the spray at the outside edge. If the craft rolls to one side and actually sticks rolled to one side, then the problem is usually caused by the hull shape, Coanda effect on a rounded surface sucking that side in, the vertical center of gravity being too high, or the longitudinal center of gravity being too far forward, which then causes the forward curved surfaces to be wetted and the Coanda effect can come into play. Chine walking, where you're walking from side to side, is slightly different. The craft is trying to stabilize itself. It falls over and it comes back upright. But there's too much or too little righting moment, and so usually there's a bit too much and not enough damping, so that it's overcompensated. It rolls to the other side, which kicks it back. and you can set up an oscillation. It needs more research. You can get some answers if you tank test models. It's very difficult to get any answers on the drawing board in a design office unless you do some actual tank testing. Maybe CFD will start to help us. But a lot of it is damping, and a lot of it is to do with the roll moment of inertia of the boat and the natural frequency in roll. If the writing moment inputs coincide with the natural roll frequency, then you can get this oscillation set up, and that can obviously get worse. It applies to non-stepped hulls as well as stepped hulls, so it's a general problem. This is a sort of idea. There's a craft running light and high. You deflect. If you haven't got the chine in the water, use a spray rail to catch the outer edge of the spray. If you need more input, this is exaggerated, but you can put a down angle on the rail. You can put the down angle on the chine. It depends which one's working. If you've got a roll or chine walking problem, you'll find that one or the other of these will do the job. If you do them both, if you do that one first, the spray rail first, and then do the chine rail, if that one causes an improvement, this one will hardly improve it further. If that one doesn't do anything, then maybe using the chine rail will do it instead. It's an experiment that you have to do on the actual boat. So reduce the height of the vertical center of gravity, increase or adjust the writing moment from the chine on the spray rails, the way I was describing in the picture. And this is often coupled with yaw. If you get in a boat that's chine walking, you don't often think of the fact that it's yawing from side to side. But in practice, in the truth, it is probably doing that. And you know that if you turn a V hull, it will bank. If you turn it the other way, it'll bank the other way. So tied in with this oscillation moment is a wriggle of the boat in yaw. So if you, even if you can't feel it, even if it just feels like chine walking, if you improve directional stability, bigger rudders, bigger fins at the aft end, make sure the steering has got no slop in it, very important, then that can often help chine walking problem. Oops. Excuse me. Can you still hear me? Good. Decisions you have to make, same as for non-step boats, but it just gets more complicated. Calm water speed versus rough water performance. The further aft the center of gravity, the less the resistance. The further forward the center of gravity, the better the rough water ride. But for each of those positions, the ride and resistance are usually improved over the non-stepped hull. More decisions, the number of steps you put in the boat, the longitudinal position, the longitudinal positions of those steps, the actual height of the steps, and the step shape in plan view. People have different opinions. I emphasize I'm giving you my opinions on these things. Weight and hull loading, of course, that affects the number of steps, the speed you're going, the dead rise, the longitudinal center of gravity position, and ventilation. I'll just put my picture up here again. You can see some channels across here behind the steps. It's important that steps are ventilated. There's a channel in either from inside the boat through tubes, but that's complicated, or a channel from the outside into the back of the step here. Because if it doesn't ventilate, atmospheric pressure pushes all the water along with you, so you find you're dragging the whole ocean, and the boat stops dead. So it's an important aspect, although it's not usually a problem with monohulls. It can be a problem with catamarans or multi-hulls, trimarans, where the chines are well below the surface when the boat's static. With a deep V style monohull, the chines are usually pretty close to the static waterline anyway. Lift and drag. I use a modified Savitsky system because I don't know any other way of doing it, but you can't buy it anywhere, or we can't buy programs for it. You have to do your own. Daniel Savitsky, who created this very useful system, emphasizes that it's not designed for the speeds that we make boats run at. So you have to put your own fiddle factors and things on it. With a step tile, you have to go further, you have to split it up. Why split it up between the surfaces? And you have to combine the effects of all these. So how do you work out the wetted lengths of the surfaces, i.e. the wetted areas? These are the wetted lengths. So you've got to, in order to work out the wetted lengths, you've got to work out where the leading edge is of those wetted lengths. So the paths, the streamlines, the water's heavy stuff, doesn't like to move out of the way. So if you're just on the plane, at displacement speeds, of course, you move solid water out of the way of the ship and the craft. At lower planing speeds, there's still quite a chunk of solid water being shifted. And so the streamlines of the water leaving each step can leave at the angle of the buttock line, the angle of the hull surface ahead. So it drops down and then climbs back up again. And Savitsky and Clement have, and others have produced formulae for working out what the shape of that surface is. But in my opinion, at higher planing speeds, the water doesn't move at all, solid water. It doesn't have time to. It doesn't realize the boat's coming. The boat arrives and it's taken by surprise. So what the forward surface does is just take that upper layer of water and chucks it out of the way as spray. He just throws it aside. So it's all spray. It just converts it into spray, folds it away across the top of the surrounding sea. So the underlying solid surface doesn't move. So you get this area here, chucks this top layer. I should have done this in layers. I'm sorry about the pink water. It works. The theory works in blue water as well. You chuck the spray off here. So you scrape the surface off. So the underlying surface lines up with that level. And that careers into the next surface. That scrapes off the next layer, depth of water as spray, chucks it out to the side, bouncing it off the rails here. And the underlying streamlined surface then that matches up with that carries straight on, in my opinion, parallel with the horizon, if you like, until you hit the next surface aft. Now that theory may not be, it's a theory I use, it may not be strictly accurate, but I think it is more accurate than using other systems for once a craft is well and truly on the plane and running fast. Gives that sort of shape, as I said before, so that you've scraped all this off the spray. The underlying streamline that lines up with that goes straight back to that corner, straight back to that corner, and in between. And the same back here, straight back, straight back. So you then have to balance all this up, and it's an iterative calculation, which you have to do with monohulls too. So you take all your lift, drag, center of pressure on each surface. You need the aero lift, drag, center of pressure, plus the same for all the appendages you're dragging through the water, and your thrust lines. And the final lift resultant must be under the center of gravity. So the results of all these forces have got to be under the center of gravity. So your spreadsheet program or other program or whatever system you're using has to iterate between different trim angles of the boat until all these forces line up. It's the same as for a non-stepped hull, but it's more complicated because you have to do it for each surface. And there are other complications on how you treat wetted lengths. Well, we've done the wetted lengths, but how you treat Reynolds numbers and funny things like that. What Reynolds numbers require an underlying length distance. And there's some controversy as to how you do that. So in the future, CFD is getting closer, but my feedback is it's not reliable yet, although we're trying. It works better at some speeds than others, the results are. I've been working with Navitec in Hawaii who are very good at their CFD. And I've been using my old-fashioned Savitsky system, adapted myself, and producing drag and lift figures my way, firing them over to Navitec, and they've been applying their CFD to it, and we've been seeing how close they are to each other. Basically, we're getting closer to each other. But I emphasize which of us is the closest to right. Should they be getting closer to me, or should I be getting closer to them? Don't know the answer to that yet. So thank you very much. That's the end of that.